So part D is asking us for an error bound. So it says that we have this Maclaurin series. They tell us it converges, and it says we have alternating sign, we have decreasing in absolute value to 0. And then we want to use the alternating series error bound to show that the approximation differs from h of 1 by at most 0.45. So you have to remember what this alternating series error bound is. It's that if you have an alternating series and it converges by the alternating series test, which means that the terms are strictly decreasing and their limit is 0, then that series converges by alternate series test. But furthermore, you get an error bound. And the error bound is that the error is less than or equal to the absolute value of b sub n plus 1. That's the error for the nth term, let's say. All right, so what we have to do is look at where all these terms come from and say, all right, well, what would have been the next term? That's what we're really looking for, is what would have been the next term. So if I think of this as being n equals 0, n equals 1, n equals 2, n equals 3, what would have been n equals 4? What would have been b sub 4? So we see, our third degree error term is less than or equal to the absolute value of b sub 4. We need to find out what b sub 4 is. So in order to do that, we need to backtrack and say, where did these things come from? So if we go all the way back to the beginning here of what our f of x was, this is your n equals 0, n equals 1, n equals 2, n equals 3. If I want n equals 4, I need the next derivative, because remember these numbers, 3 halves x squared and all those, they came from these numbers here. That negative 23 twelfths, it was negative 23 over 2 times 3 factorial. Right, so what we're going to have for our n equals 4, see, this is why they gave us the fourth derivative. So for our n equals 4, we're going to have 54 over 4 factorial x to the 4th power. Because, right, this was f over 0 factorial, f prime of 0 over 1 factorial, f double prime of 0 over 2 factorial, there's your f double prime, f triple prime of 0 over 4 factorial, and then this is f4 over 4 factorial, f4 over 4 factorial. All right, so, and then we get to the x to the 4th. So that's just adding another term from, for the Taylor series. All right, so but then that means that where that had to have occurred is here in this integral. So for my n equals 4, I need to be looking at the integral from 0 to 1 of this term, 54 over 4 factorial. We're going to go with t now, t to the 4th dt. All right, so I need to look at what the antiderivative of that is. So it's going to be, so I'm going to have 54 over, so I'm going to have t to the 5th, and then I'm going to divide by 5. And if I multiply 4 factorial by 5, I'm going to get 5 factorial. So I'm going to have here is 54 over 5 factorial t to the 5th from 0 to 1. So that's going to be our B4 term. And that's what we're headed toward here, is getting what B sub 4 is. So then when I plug in the 1, I get 54 over 5 factorial. When I plug in the 0, I get 0. So that fourth, I guess it's the 5th term, which is corresponds to n equals 4, since the first term is n equals 0, is just going to be 54 over 5 factorial. So that's what B sub 4 is. So that's what we could put here. That absolute value of b sub 4 is 54 over 5 factorial, and that's 54 over 120. So I can divide the top and bottom by 6, and I get 9 over 20, and that's 0.45. Right, I don't need a calculator to tell me that 9/20 is 0.45. I can work that out pretty easily. This is a no calculator question, by the way. All right, and then, so I have shown that the approximation found in part C differs from h of 1 by at most 0.45, because this is the error bound for the third degree polynomial, which is what we had for part C, and we've shown that the error bound is less than whatever the 4th term would have been, or the the 4th degree term, and we figured out that that 4th degree term was going to be 0.45.